In section 3.4, we'll explain independence of basis and dimension. And first, we'll cover a linear independence. We already know what is linear independence, but here is a definition. Columns of A are linearly independent then if and only if AX is equal to 0 has the only solution x equal to 0 vector, and null space has only the 0 vector. So, well, I don't think it's definition. I think it should be a theorem. So I think it's better to write as a theorem. But this is rather obvious because suppose we have this equation a1 and so on an. These are column vectors, and we consider this equation, and so this is just we compute using a column way, and then we have this equation. So if the columns of A are linearly independent, there is only one way. I mean, we have only a trivial solution. So because this is the definition of linear independence, and so this is the only solution. So O0 solution. So that's why we have this. AX equal to 0 vector has the only solution. And the null space, the element of null space satisfy this equation. And so null space has only the 0 vector. So the homogeneous equation is connected to a linear independence of the column of matrix. So the definition of linearly independent is this one. Suppose x1 v1 plus and so on xn vn is equal to 0 vector, and then the solution is just this O0 solution, xn is equal to 0. And then we say the n vectors are linearly independent. We said why this is true, because if we have any non-trivial solution like xi is not equal to 0, and then we can write xi vi and k is equal to 1 to n, and k is not equal to I, and minus x k vk. But because xi is not equal to 0, so what we can do, we divide by xi. So we have vi is equal to minus x I 1 over xi, and k1k is not equal to I, and xk vk vector. So we can represent vi as a linear combination of other vectors. So in this case, So that shows that a vi vector is not essential because it could be generated using other vectors. So in that case, we can say this set, the vectors and vectors are linearly dependent. In this case, we can say that they're dependent because one vector could be generated with other vectors. Now we see some examples. We have two vectors, 1, 0 and 1, 0.001 are independent because the other vector is not the multiple of the other vector. And B, 1, 1 and minus 1, minus 1. Obviously, they're dependent because when you multiply minus 1 to any vector, so then we get the other vector. And 1, 1, 0, 0 will be dependent. And you have to know that if I say if you consider a zero vector, and if you consider a set that include a zero vector, and then we can say the set is always linearly dependent because the coefficient, when you make a linear combination, the coefficient could be non-zero. So it's a non-trivial linear combination, and in that case, I mean, using a non-trivial combination, you can still generate a zero vector. So in that case, the vectors are linearly dependent. D, A, B, C, D, and E, F. So in this case, we don't have exact number, but we're pretty sure these are dependent. The reason is that these three vectors from two-dimensional space. So we didn't define the dimension yet, but that's why we select three vectors, and in this case, they are dependent. Or we can just make an equation like this: A, B, C, D, E, F, and we want to find x1, x2, x3 for this homogeneous equation. But in this case, there should be free variable. There exists a free variable. Because we have three variable, but the maximum number of pivots, it's only 2 in this case. Because the rank should be less than or equal to the number of rows and number of columns, and that's why we have at least one free variable. So we have a free variable. That means there exists a special solution. I mean, special solution is not a zero vector. It's a non-trivial solution. In this example, we can see that this homogeneous equation has a non-trivial solution, which is minus 3, 1, 1. So we have a non-trivial solution for this homogeneous equation. So in that case, we can say columns of A are dependent, because non-trivial solution generates a zero vector. So we can say columns of A are dependent, and in this case, the rank of A is equal to 2, because we can immediately see that these vectors and these vectors are independent. Obviously, it's not the same direction, but we have a non-trivial solution. So there should be dependence. So we'll explain about vectors that span a subspace. And let's see example 2. And describe the column space and the row space of a matrix. And the column space of this is just a linear combination of columns. So column space is just this. And C1 and C2 is an arbitrary real number. And row space, this is C A transpose, which is C1 1 4, C2 times 2 7, and C3 times 3 5. This is just a definition of row space. C1 and C2 and C3, they're all arbitrary real number. Actually, this is all 2. Because 1 4 and 2 7, they are linearly independent because they're not in the same direction. So actually, the 3 5, the last column, last row is not necessary to span the space, R2 space. Now we'll define a basis for a vector space. A basis for a vector space is a set in a vector space that satisfies 2 things. One is the set should be linearly independent, and also it has to span vector space V. So to be linearly independent, the number of vectors should be small enough. If you have too many vectors, usually the probability that that will be linearly dependent will increase. So but in that case, if you have just 1 or 2 vectors and 1 or 2 non-zero vector, and we are pretty sure that it'll be linearly independent. But the problem is it's not enough to span the vector space. To span the vector space, we need more vectors because we need generator. So the 2 constraint, we can have a basis. So it should be large enough to span the vector space, but it should be small enough to be linearly independent. So if you have a vector space and we want to find basis beta, you have to be very careful. Beta is not unique. There could be many bases. Some bases are we like that basis, but sometimes we don't like that basis. So we'll learn that. But in many applications, eigenvector basis it's really important. But anyway, a basis is not unique. There is only one way to write a vector in the vector space V as a combination of the bases. So there is a unique way, and we know that there exists a linear combination for any vector, because if you say a basis spanned V, that means we can generate any vector in a vector space using that basis. So we know the existence, but we can prove that the uniqueness using a linear independence property. So suppose that a V vector, any vector V, is a linear combination of this basis. And we assume that there is one more linear combination, because we're going to prove the uniqueness. So there is only way. So this is only one way. That means this is uniqueness theorem. The way to prove the uniqueness theorem is very simple, because we assume that there are two, but and after that we just some calculation, and then we conclude that they're the same, because we assume that there exist two solutions, but if they're equal, so we can say there is only one. So we assume that there are two linear combinations for a vector v, and so we subtract each term. We have 0 vector here, and a1 minus b1, and so on. An minus bn, vn vector will be 0 vector. But as we know, because these vectors are bases, so the vectors are linearly independent. That's why this is A. And so linearly independent, so only one possibility is a1 minus b1 is equal to, and so on, an minus bn should be 0. Otherwise, the v1 and so on and vn, they are dependent, because when you think of this equation, we have only a trivial coefficient when the vectors are linearly independent. So a1 is equal to b1, and now we know that an is equal to bn. So there is only one way. I mean, the linear combination is unique. 1, 0 and 0, 1 is the standard basis for R2. And as I said earlier, we have many bases for R2. For example, 2, 0, 1, 1 could be a basis, and 100, 200, and 3, 5 could be a basis. There are many bases. As long as they are independent, they are all bases. But as I said, this vector 1, 2, and 0, 0, 0, 0 could not be a basis, because if you include 0, 0, 0 vector, and then immediately the vectors are dependent, and so this could not be a basis. And for example, 1, 2, and 2, 4. Oh, this is not a basis, because they're independent. Just multiply a 2, and then we can get a 2, 4. So in this case, this is not a basis. This is not a basis. Oh, I mean, this is not a basis for R2. Yeah. So given vector space, we are looking for a basis. So you have to know what we are talking about. So I mean, we have to be given a vector space. Then we try to find the basis. And every invertible n by n square matrix, because invertible matrix are always square matrix, so this n by n is not necessary. But anyway, every invertible matrix of columns give a basis for Rn. The reason is that invertible means that we have independent columns or independent rows. And So column space will be Rn. So that's why. For example, if A is equal to 1, 1, 1, 0, 1, 1, 0, 0, 1, and this is, we can see that the columns are independent. So this is invertible matrix, and in this case, 1, 1, 1, 0, 1, 1, and 0, 0, 1 is a basis for all three. If n by n matrix, n by n matrix is singular, is not invertible, then the columns will be dependent. And then in that case, a column space of a matrix is not equal to Rn. So we can say Vn is a basis for Rn is an equivalent solution, equivalent to the statement of V1, I'll write down as a vector, V1 as a column vector, V2 and Vn is invertible. There are some properties. I'm not going to prove that. Every set of independent vectors can be extended to a basis. So if you have just a small number of independent vectors, you can add some more, and then you can find a basis that include the previous set. And every spanning of vectors can be reduced to a basis. So I said before, to be a basis, the set should be large enough, large enough to generate all the vectors in the vector space, and also the number of vectors should be small enough to be linearly independent. So in case 1, we have too small number of vectors, and so we need extension. We need to add more vectors to be a basis because we don't have enough generators. And a number 2 case, this case is that we have already too many generators. In that case, because too many generators mean the vectors are right now dependent. So to be independent, we have to reduce the number of vectors. But this is an important theorem, but the proof is quite long, so I could not include that proof. We see this example. This matrix is singular. This is not invertible because determinant of A is 2 times 6 minus 4 times 3, which is equal to 0. And so 2, 3, and 4, 6 is dependent. So not a basis. Not a basis for L2. And A is 2, 4, 3, 6, and I think it should be 4. And after Gaussian elimination, we get 1, 2, 0, 0, because this is reduced row echelon form. So after elimination, and then we make the pivot is equal to 1. But anyway, we have only one pivot. And so columns are dependent. So only one pivot. So columns are dependent. And we have matrix R0 here. And we can see we have two pivots. And we want to find the basis of the column space of R0. But we see that columns 1 and 3 are pivot columns. So columns 1, 3 is a basis of CR0. And CR0 is a subspace of R3. Because we have only two vectors, so it could not be the same. But we have to be careful. CR0 is not R2. Only the dimension is the same. We didn't define dimension, but now we can define that. Dimension of vector space is just the number of vectors in a basis. So what I mean is that this 1, 0, 0 and 0, 1, 0 is a basis of CR0, column space of R0. But if you write 1, 0, 0 and 2, 0, 0, this is column 1 and column 2, is not a basis. Of CR0 because these two vectors are dependent. Now we have a question. Given 5 vectors in R7, this is 7, how do we find a basis for the space they span? So we have to be careful for the space they span because we have only 5 vectors. So a maximum dimension will be 5, but we don't know whether they're independent or not. If they're dependent, maybe the dimension of the space they span will be less than 5. It'll be 4 or 3, anything is possible. And the first method is we write a matrix with row A1 transpose and A2 transpose and so on. A5 transpose. And after Gaussian elimination, we see a non-zero rows. So these non-zero rows are a basis. a basis, no, I think so, we said R, so it's confusing sometimes, are basis vectors. That is better. Basis vectors of the row space. So in this way, we can find a basis for the space they span. The important thing is Gaussian elimination does not change row space, but a Gaussian elimination changes a column space. So when you want to find something related to space, you need to write the vectors as rows. Otherwise, when you apply Gaussian elimination, the column space will be changed after some elimination step and elementary row operation. Yeah, because the operation is basically a row basis. So I mean. Just multiply rows, the number to rows, and then a subtraction row by row, and that's why the column space will change after elementary row operation. So if you want to find directly the basis, and you need to write the vectors as a row vector. But there is the other way. The other way is you put the column as it is. Just write column by column. And then you apply a Gaussian elimination. Elimination. But as I said, if you apply a Gaussian elimination, the column space of a matrix will be changed. But we can still find the pivot columns. So pivot columns of A is basis vectors of the column space. You should be very careful. I mean, you just select the location. I mean, just an index from the Gaussian elimination. From the Gaussian elimination, you just find the pivot columns. I mean, the location of the pivots. And then after that, you select the pivot columns of A. After elimination, you will find R0, but don't pick R0. Any column in R0, because the column space is already changed. So what we need is just an index information, the location of the columns, and then the pivot columns of A will be basis vectors of the column space. A given vector space, all bases contains the same number of vectors. So as I said, if we have a vector space here, and we have a basis, and for the same vector space, we could have another basis. So the basis is not unique. But invariant thing is that the number of vectors in a basis, it's called dimension. In mathematics, the invariant is important, because invariant means that something inherent thing. For example, you remember when you have a cube and any 3D a polygon you know the Euler number, number of vertex minus number of edges plus number of faces will be 2 for any like pyramid shape. I don't know, maybe this one also has that property. The vertex, a number of vertex minus number of edges plus number of faces will be 2. So this is kind of invariant because always it's 2. This number is always 2. So this is a special number. And similarly, I mean, a basis could be many. You know, that its basis is not unique, but the number of vectors in the basis is always the same. So it's a special. So we gave a name for that. It's dimension of a vector space. As I mentioned before, the concept of basis is quite similar to periodic table, because in periodic table we have many elements, and for example we have hydrogen and oxygen, and we 2H plus O, we say maybe we need some energy, but H2O is generated, and so this is kind of generation using element, some fundamental element. We generate something, and for example, another example is a prime factorization, and so for example, as a 12 is 2 square times 3 1, and we can say 12 is composed of 2 and 3. So we generate using 2 and 3. So in this case, periodic table case, elements are some kind of basis, and in prime factorization, prime number is a kind of basis. But in mathematics, basis is not unique. So in that sense, it's different, but the concept is quite similar. Dimension of a vector space is defined as a number of vectors in every basis of V. See the example. The line through V vector, and we assume that line through V, and also it's line through 152, and also origin 0 0 0. So this is a vector space, so we can say this is V. And what is the dimension? A dimension of it, dimension of V is because this is the line and this is 1. And W is the perpendicular plane to V vector, and we also assume that this plane goes through the origin 0 0 0. So this plane has dimension 2. This is W, and this plane is the null space of matrix 1 5 2. Because this plane, the equation will be like this: is x1 plus 5 x2 plus 2 x3 is equal to 0. And this is the plane. And so this is the null space of this matrix. And sometimes in other textbook, a null space or kernel is okay, but in this textbook by Gilbert Strang, we call it just null space, but the kernel is okay. So A has two free variables. So if I write this equation, I mean a x1, x2, x3 equal to 0, and obviously x2 and x3 will be a free variable, and so the special solution, a special solution of this equation will be S1, and which is 1, 0 here, and S2, which is 0, 1 here. And we can find x1 using this pivot equation, x1 plus 5x2 plus 2x3 is equal to 0. And then we can find value of pivot variable. And this is the special solution for this equation. And so n minus r special, in general, special solution, n minus r special solution of ax equal to 0 vector, and the size of A is m by n, is a basis for the null space of A, and dimension of null space will be m minus r, because we have m minus r basis vector, and dimension of column space, which is C of A, or C of A transpose, which is row space, is the same, and this is just the rank of it, the rank of the matrix. Now we'll consider basis for matrix space and function space. First example is about function space. Y double prime is equal to y, and we plug in y is equal to exponential e to the lambda x, because we guess that after differentiation, still the form of function doesn't change, so we can expect it could be the solution is a exponential function. That's why this is a guessing of the solution, and then we plug in, and then we get lambda square e to the x, lambda x is e to the lambda x. So we have this equation, lambda square is equal to 1, so lambda is plus minus 1. So e to the x and e to the minus x is a basis of the solution space. So the answer to this differential equation will be the solution is y of x is equal to c1 e to the x plus C2 e to the minus x. And C1 and C2 will be any number. And a dimension of solution space will be 2, because we have two function. So that's why we have solution space is just number 2. We will consider a 2 by 2 matrix. So the element of this vector space, the vector in this vector space is just this matrix, and the dimension of this vector space is 4, because a basis of M, we can call this just matrix space, because the element of vector space is a matrix, and so maybe we can call it matrix space, but well, we can still call it vector space. A basis of this M is, it could be a beta consists of 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. And maybe we need to prove that this is a basis of M, and we need to prove 2 things, whether span of beta is equal to M, and we need to check beta is linearly independent. And then we can so the proof is done. So number 1 proof, number 1, and we can prove easily that if we select any matrix in the vector space, we can generate anything. We can generate any matrix using this basis, C3 times 0 0 1 0 and C4 0 0 0 1. So we can find any element. We can generate any element as a linear combination of this 4 matrix. So 4 matrices. So number 1 is proved in this way. To prove that these 4 matrices are linearly independent, we need to prove in this way, because suppose the linear combination of these 4 matrices is a zero vector, a 0 matrix, and then we can see that C1, C2, C3, C4 is equal to 0 0 0 0. So we can see that C3 and C4 is equal to 0. So we proved that. What we proved is that 1 0 0 0 and 0 1 0 0 and 0 0 1 0 and 0 0 0 1 is linearly independent. In this textbook, is not so rigorous. So when basis was mentioned, it's basis is not a set. Just say basis vectors and something like that. But in a rigorous textbook, usually a basis is a set. So I stick to some kind of a rigorous notation. So that's why I always show this a set notation here. And U is a 2 by 2 upper triangular matrices, and this is a vector space because adding a two upper triangular matrix will be an upper triangular matrix, and if you multiply a scalar to any upper triangular matrix will be also upper triangular matrix. So U is a vector space because it's closed under addition and scalar multiplication. And what is a basis? Any basis? Well, it's pretty easy because upper triangular matrix are in this form, A, B, 0, C. So the basis will be 1, 0, 0, 0, and 0, 1, 0, 0, and 0, 0, 0, 1 will be a basis of this a vector space, which is upper triangular matrices. And so dimension of U will be 3 because we have 3 vector. Well, I'm calling this just vector because it's an element in a vector space, but you can call it just matrix because we can call it just this is a matrix space. D is the set of 2 by 2 diagonal matrices, and we want to find the basis and the dimension of it. And what is D? So 2 by 2 diagonal matrix like this, and this is a element in D. And so a basis beta could be this one, 1, 0, 0, 0, and 0, 0, 0, 1. Because as a linear combination of two matrix, we can generate this matrix, and also the two matrix is linearly independent. And so the cardinality of beta is 2, so a dimension of D is equal to 2. In general, dimension of n by n matrices will be n squared, and dimension of n by n upper triangular matrices will be 1 plus 2 plus and so on up to n, and it'll be n plus 1 divided n plus 1 divided by 2. So n by n diagonal matrices, for diagonal matrices the dimension will be n because the number of diagonal entries is n. And for n by n symmetric matrices, the dimension will be n times n plus 1 divided by 2 because in this case, symmetric matrices, the basis will be this because the element in the symmetric matrix will be this form, the A, B, B, C, and so the dimension is for symmetric matrices is equal to the dimension of upper triangular matrix. Now we will consider function spaces. For example, so it's a solution spaces, a solution space of differential equation. If we have a differential equation y double prime is equal to 0, the solution will be this line, y is equal to cx plus d. And if we see this differential equation, the solution will be the linear combination of sine x and cosine x, and you just plug in, and then you can verify that it's a solution. If you don't know how to solve a differential equation, it doesn't matter. We just want to show solution space is just a vector space. And y double prime is y. For this differential equation, the solution will be c times e to the x plus d times e to the minus x. And so we can say a basis of the solution space of differential equation y double prime is equal to minus y will be sine x, and cosine x. Similarly, a basis of the solution space of y double prime is equal to 0 will be 1 comma x. We can write this differential equation in this way. I mean, in this way, we use the d as a differentiation operator. And in this case, cx plus d, and c and d is an arbitrary number, is the null space of the operator d square. As another example, if we have y double prime is equal to 2, and then solution is not a vector space. It's not a vector space. So we cannot say a solution space because the solution is not a vector space. Because the solution of this equation will be y is equal to x squared plus cx plus d. And you can see that structure. Because cx plus d, what is it? This is a solution of y double prime is equal to 0. And what is this? And this is a particular solution. A particular solution of differential equation, which is y double prime is equal to 2. And so we add a null space solution, and so now we have the complete solution of this differential equation. But the solution is not a vector space because of the non-zero particular solution. This is the trivial vector space because it has only the 0 vector. And I need to mention that because when I ask a question in any midterm exam or final exam, what is the basis? What is the basis of? I should mention it's a basis in general, but it's the basis, the right one. But what is the basis of Z? And the answer is empty set. So empty set is the right answer. And sometimes some students write the answer like this, or just a 0 vector is a basis, but it's a wrong answer because a 0 vector cannot be a member of basis. So it's not a basis because if you include any 0 vector in the basis, and the set will be linearly dependent because you can write a non-zero coefficient in the linear combination. So zero vector cannot be cannot be included as a basis. So it's a very important thing. So this trivial vector space, which has only the zero vector, what is the basis? And then the answer is just empty set. This is the end of the lecture for 3.4.